Good afternoon, class. Let's get started. So last class we introduced a new coordinate system for looking at the same physical laws and same frameworks and same lenses that we've been looking at the world all semester. So today/Friday, maybe the Monday after spring break, I'd love to wrap up sort of what I'm calling the first half of this semester. That is the half of the semester where we're talking about trains and spaceships and satellites and moons and planets and kind of the big moving parts of the world. And we're going to spend the rest of the semester talking a little bit about modern physics, hopefully, but also about some of the more ephemeral, invisible parts of the world, like cell phone signals and things like that. Okay. So the first thing I wanted to review and to stress is that we've spent several weeks in this class looking at Newton's laws, and then looking at work and energy, and then looking at impulse momentum. What we're doing now is not really looking at anything new. Really all we're doing is just changing the coordinate system. And that's really just about all that's new. And so we're still looking at Newton's laws. Newton's laws still apply. Newton's laws still work. F equals ma still works. Work and energy still applicable, so is impulse momentum. We've just changed our coordinate system. And the reason for that is when we're talking about things like spaceships going in circles, or bicycle wheels going in circles, or anything else that goes in a circle, it's much more convenient to not use x and y linear dimensions. So as I mentioned last class, my pink poof ball right here could be described, its position, velocity, and acceleration could be described right now with x and y coordinates. But its x coordinate, if we call this x, if we call the horizontal x, its x coordinate is going, well, it's moving around on me. Its x coordinate is going that way, that way, that way, that way. It's changing constantly, and therefore it must be going under some constant forces in the horizontal direction. Same with the y direction. And its speed is changing. Its speed is going this way, now its speed is going that way, now its speed is going up, now its speed is going down. That is difficult to do. Doable, but difficult to do. We can make our lives a lot easier if we adopt a new coordinate system. The new coordinate system is the angular coordinate system. So I can describe that same pink poof ball just by saying it's got some angular speed and it's at an angular radius, or it's at a radius. That's it. So my pink poof ball pretty much has a constant angular speed right now. Instead of saying it's going left, now it's going right, now it's going left, now it's going right, I just say it's going angularly. It has a certain angular speed. It's going about, I don't know, 2 or 3 radians per second. And so the same measures of, so in the linear realm, we have position, we have the rate of change of that, and the rate of change of that. That's position, velocity, and acceleration. In the angular realm, we have displacement, we have the rate of change of that, and we have the rate of change of that. It's the same idea. So I've got where this thing is angularly, let's call that 0, let's call that pi over 2, let's call that pi radians, and let's call that 2 pi. So that's its displacement. How quickly it's changing that is just its angular velocity. It's going through a radian roughly every second right now. A radian's up there. A radian is just how far along the path one radius would be. So like yay far. So I don't know. That maybe right there is about 1 radian per second. Okay. We'll talk about how you have to apply torque to a door to open it. And so it's got a hinge, and you need to apply torque, which is a force acting over a distance if you want to open doors. Comes in handy. Okay. So we've got position, velocity, and acceleration. We talked about that last class. That's pretty straightforward, I think. So I've got angular position, radians. Angular velocity, we use lowercase omega. And angular acceleration, we use lowercase alpha. And that's just the position, rate of change of that, and rate of change of that. Things get a little more complicated when we're talking about mass. So mass, a good definition of mass is something's resistance to being accelerated. So m equals F over a, right? And so if something is massive, it doesn't want to be accelerated. And that's a pretty good definition of mass. We measure that in kilograms. So a kilogram, your kilograms is just a measure of how much stuff you have. I have, it's been a while since I did the math, I don't remember how many, a lot of carbon atoms and hydrogen atoms and oxygen atoms inside my body and other types of atoms. Each one of those atoms has mass, and each one of those atoms, because of its mass, has a certain resistance to being accelerated. And so if you were to grab me and try to accelerate me, there's some resistance there. You can't just throw me at the speed of light across the room. I have some resistance, that's my mass. Now if you were to try to throw me across the room by my feet or by my arm or any other part, it's going to be the same difficulty because my mass is my mass regardless of whether I'm in a ball or like this or what side, where you're holding me. It's the same thing. In the angular realm, there is also resistance to being accelerated. So if I want to accelerate this thing angularly, or if I want to accelerate my bicycle wheel angularly, there's resistance to that. Or decelerate it, there's resistance to decelerating this thing. So I like to call that spinability, where I call mass shakeability. So we've got shakeability down there on the left and spinability down there on the bottom right. Shakeability and spinability. Your resistance to being shaken or spun. And so this thing takes effort to spin up and spin back down. So it takes effort for me to get it going, and it takes effort for me to slow it down. And that is a product of how massive it is. This is a good kilogram or so, but also how the mass is arranged. And like I said last class, you can see in the units, the arrangement is even more important than the mass. The arrangement, how hard this thing is to spin, goes up with the square of how far away the molecules are, or the mass is, from the axis of rotation. So if my axis of rotation is way down here, some of the aluminum atoms, some of the steel atoms are way over here. That's like almost a meter from my axis of rotation. This is very hard to do because I've got atoms way over here that I'm trying to accelerate through space. I can take the same kilogram and accelerate it this way, and it's very easy. Same kilogram, but right now the axis of rotation is this long axis, and no atoms are more than a centimeter or so from the axis of rotation. Much easier. That's what we call spinability. Okay. Back couple rows are having a problem with this, I think, but I'll keep going. So this is called spinability, and that's just the difficulty to being spun. Now, last class, what we just started to get into is sort of a connection between the angular and the linear realm. And this is where we ended last class. I want to pick back up. And that is, as I've said, there's lots of things in this universe that are worth describing, that are easier to describe in using angular coordinate system, angular ideas, angular measures, because they go in circles. So things like astronauts. So there's an astronaut floating, I guess you could say, in space, or at least orbiting the Earth. And there's Commander Scott Kelly and some apples also floating or orbiting in space. Commander Scott Kelly just got back yesterday. I don't know if you heard. He spent a year in space. I think that was the longest continual run of any American, if I remember right. But he just spent a year in space, and he just got back yesterday. And so there's a picture of him and some apples in space. Those Commander Kelly and those apples are going in a circle. Here's your big lesson of the day. This is probably the big one of the day. Stuff doesn't go in circles by itself. When Newton said, so an object in motion tends to stay in motion, he said in a straight line. So your big understanding of the day is if you ever see anything going in a circle, something is pushing on it. That is, you can take that to the bank. Nothing goes in circles by itself. So if you were to watch my poof ball right now, it's going in a circle. Things don't do that by themselves. I can observe that system right now and be very sure some force is acting on that poof ball. Things do not go in circles by themselves. Commander Scott Kelly does not go in circles by himself. Something is pushing or pulling on him. I can be sure about that. I can watch those apples. So right now, if I were to watch those apples, they're going around the Earth in a circle. They're going around the Earth. They're orbiting the Earth. Things don't do that by themselves. And so this whole circular motion thing, I can draw some conclusions when I see things going on in circles. And so often, I want to look at a situation like that and go, what is the thing doing the pushing or pulling? And we started talking about that last class, that things in this universe tend to go in straight lines if nothing else is acting on them. And so if I imagine that astronaut on the top left, if I imagine him just floating like that, he must have no forces acting on him. You can float around like that. You have to be really, really, really far from any planets. You have to be hundreds of thousands of miles away from a planet of Earth size if you want to just float around. So an astronaut floating around like that, it could happen. He or she would have to be out in interstellar space way far from nothing, and then they would just float around. That'd be great. That astronaut is only 250 miles or so above a really big rock called Earth. And if you're only 250 miles from Earth, you are going to accelerate toward Earth at about 9.8 meters per second. 9.6 or so from where that guy is. So in other words, fall like a rock. Or another way to say that is that astronaut is feeling a force. That force is called his or her weight. So that astronaut is not weightless. I think that's a bad term to use for astronauts that are anywhere near a planet. They're not weightless. That astronaut is weightful. That astronaut weighs about as much as they'd weigh on Earth. And so if you have one force acting on you, your weight, you're going to start accelerating at about 9.8 meters per second toward the center of the Earth, which, in the case of orbits, is absolutely necessary. So let's talk about things in orbit. Anything going in a circle, things don't go in circles by themselves, is experiencing a force. And that force, here's another conclusion we can draw. So if I see something going in a circle, I can draw a couple conclusions. One, there's a force acting on it. Two, that force is centripetal. Centra meaning center, pet meaning seek. So if you've ever signed a petition, you were seeking something. If you've ever been in competition with anyone, you were co-seeking something. You both wanted to score a goal or whatever. So pet means to seek. And the reason I am explaining that is because people very easily confuse centripetal and centrifugal. To fugue something is to flee. Fugitives are fleeing. So centrifugal is fleeing the center. Centrifuge means you're running away from the center. So if I were to draw an orbit of like the Earth or something, a centrifugal or centrifugal force would be pointing away from the center. A centripetal or centripetal would be pointing toward the center. So hopefully we can start clearing up that misconception. And here's another misconception. So centrifugal forces don't arise very often. And so that astronaut is not experiencing any centrifugal forces. A centrifugal force, centrifugal, would be throwing that astronaut away from the Earth. That's not what's going on. That astronaut is experiencing a centripetal, center-seeking force. And so if you are going in an orbit around a planet, there is always a force, it's called weight, connecting you to that planet. That's convenient, because to go in a circle, you must have a centripetal force. If you ever see anything in this universe going in a circle, it is experiencing a force, and that force is centripetal. It's pointing right at the center. And so if you were to just take an astronaut, I said this last class, if you were to take an astronaut and just deposit him or her in space and let him go, that astronaut would feel a force directed toward the center of the Earth, and you would see that astronaut accelerate toward the center of the Earth. If you were to take an astronaut, and here's how we actually do it. We don't do that. We don't just drop guys off and say, good luck. We blast them off the Earth, and we steer the rockets. If you ever watched a rocket launch live or on TV, you see it kind of do this. The reason it's doing that, it's taking a path that's going to eventually get the guy into orbit. And so blasting off into orbit isn't just getting high enough that you are now floating or something. You can't just like take somebody off Earth and go, there, you're in orbit now. They'll just fall right back down. So in order to get to orbit, you need to blast off and then get going sideways at about 17,000 miles an hour. That's 5 miles a second. That's how fast these guys are. That's one of the reasons these rockets are so big. If we just wanted to get somebody to space, if we wanted to get someone to the space station, we could use a much, much smaller rocket. We could take a little rocket, blast them off the space station, and then the space station will go by them at 17,000 miles an hour. So if we want them to be able to dock with the space station, you can't just, you can't grab it as it goes by at 17,000 miles an hour. You need to catch up with it. So any movie or we've seen this live now. Anytime you've ever seen like two things in orbit dock, it's crazy to think about. So you watch this like very slow as they come together, and then they very slowly control their velocities, and they come together and they lock together or something like that. You see that in the movies all the time, or like I said, if you ever, we have video of us doing that. We do that for real, and we just come out, and it's crazy to think what's actually happening is two things are going together at 17,000 miles an hour. Very, very precise, exact same speed. It's kind of like, I guess you could drive 100 miles an hour down the road and have another car 100 miles an hour driving down the road. And you could step from, don't do that, but you could step from one car to the other because you've matched speeds. Try doing that at 17,000 miles, at 5 miles a second. You're trying to get two big, expensive crafts to join up. It's nuts. But that's what's going on. So you're going 17,000 miles an hour. And so so as we blast people off the Earth, we get them up going 17,000 miles an hour. Now they're going so fast, yes, they're falling like a rock. Yes, they have a centripetal force called weight. But that weight is just sufficient to keep them on their orbit. And so it's a very specific speed. Slower than that, they'd spiral into the Earth. Faster than that, they'd spiral out into space. So if I want to put somebody in orbit right here, this very spot above the Earth, at 250 miles an hour or whatever, or 250 miles above the Earth or whatever, I have to get them to a very specific speed, and then I can let them go. So I get them up to that speed. There's not really air resistance or anything to slow them down. So I have enough fuel. I get them going at 17,000 miles an hour. Then I can let them go. I don't just get somebody up to 200 miles an hour or 200 miles above the Earth and let them and drop. That's kind of what Felix Baumgartner did, and you saw he just fell right back down. He rode a balloon up, not a rocket. You get going fast enough, you just never come back down. And so Scott Kelly just spent a year hanging out on the space station, and then finally just yesterday he decided he was done, and so then all you have to do is when you're up there, you're going 17,000 miles an hour, just slow down a little bit, and you'll come back down. So he takes an orbital path, and he comes back down. He landed, I think, near Kazakhstan, and we went and picked him up. Yeah, so I think there's there's our big understanding so far, is that anything going in a circle has a force going on, has a force acting on it. In terms of satellites, that force is called weight, or the gravitational force between the satellite and the Earth. There's a bunch of them. Every one of those guys is going 17,000 miles an hour. They usually miss each other. That's pretty handy. Here's another zoomed out picture. I think we have something around over 2,000 man-made satellites in space right now. So one thing I mentioned is there's a very specific speed, and that's the speed I've been using over and over, 17,000 miles an hour. I keep saying that. That's the speed of the space station, and that's one orbit, and that's very low Earth orbit. That's a couple hundred miles above the Earth. When you're going 17,000 miles an hour, like I said, that's 5 miles a second. All those astronauts on the space station, Scott Kelly and the rest of them, they get to see a sunset every 90 minutes. It's pretty nice up there. So they're going around so fast, they see sunrise and sunset. Like during this class, you'd see one or the other. So they see sunrise and sunset every 90 minutes. While he was up there, he saw 11,000 sunsets. Not bad. So if you like sunsets, become an astronaut. But that's just the very low Earth orbit. We've got other stuff other than space stations that we put up in orbit. We've got GPS satellites. So your phone is always, when you go outside, your phone's trying to figure out where on the planet it is. It's talking to GPS satellites. Those satellites are actually geosynchronous, if I remember right. Those are geosynchronous satellites. So or even if you have DirecTV or a Dish network or something like that, if you ever, or your neighbors or somebody like that have ever put a dish in their yard, they just have to put the dish in their yard and point it at a spot in the sky, and they're done. They don't have to tilt it every now and then, because we have these satellites that are actually going around. So the space station is going around every 90 minutes. It's going much faster than the orbit of Earth. If you go further out, you go slower. And we have satellites that you can see them in that picture, that are further out, that actually go in orbit with the Earth. They're on the same spot above the Earth. So I look up in the morning, and there's a satellite right there above my house. That follows with me as the Earth turns. It's up in the same spot above the sky. And so there's satellites that maybe for communication or GPS are in the same spot above the sky. Or I want to just put one right over Russia and one right over China. I can just put a satellite there, and it hangs out. So actually, in that picture, a good number of the satellites are us just spying on each other, different countries spying on each other. So the Russians got satellites over us, we've got satellites over Russia, and there's ways we can actually, so we can put them over very specific spots. We can just put a satellite right over your house, and it'll stay there. Or we can just say we want a satellite that's generally spending most of its time over Russia. And so there's certain satellites, certain orbits we'll put it in and we'll even do elliptical orbit. So it'll it'll kind of slow down as it's farther away from Russia. I think on the right you can sort of see some of those elliptical orbits. So it'll hang out over Russia, and then it'll zip around and go back to Russia, and then it'll zip around and go back to Russia. So we've got elliptical satellites that do that. But anyway, each one of those satellites, all 2,000 satellites up there on that screen, are going in a circle because they're experiencing a centripetal force. Okay, enough of that. Let's go through a couple more examples, and then I actually have a bunch more stuff we need to get to in the next 24 minutes. I hope everyone at some point in their life has had an opportunity to ride a Gravitron. That's what this is. Okay, it's awesome. It takes advantage of centripetal force. I'm going to describe what you're looking at because there's an iClicker associated with it in a second. So what you're looking at is a big cylinder. It's a big can, and it's usually at amusement parks. And you get into this can, and you put your back up against the wall, and it spins around horizontally. It spins around. And as you can imagine, you get pressed against the wall. You get pressed up against the wall. And eventually, the floor drops, and you don't go anywhere. You're stuck to the wall. So it's a big horizontal can. You can see the little riders all around the perimeter, and they spin that thing up, and they all get stuck to the wall, and the floor drops, and they stay there. It's pretty fun. And I don't love amusement park rides, and I don't get sick on those. So if you're like, well, am I going to get sick on that? Try it. I'm usually okay with those. So here's the iClicker for the day. When you're riding the Gravitron, and your back is up against the wall, and it's spinning around, you're experiencing some forces. You're experiencing normal, you're experiencing friction. That's how they work, and you're experiencing weight. I'd like to know, what direction is your normal force, and what direction is your friction force? So your normal is up and friction is centripetal, or normal is centripetal, friction is up, or normal is centrifugal and friction is up, or normal is up and friction is centrifugal. Think about that one for a second. Oh, great question. I got a laser today. This thing is spinning about this axis, this vertical axis in the middle. So all the people are looking straight at the center, and it's spinning around the center. Does that help? Good question. Yeah, up, vertical. So yeah, it's a big horizontal can spinning about a vertical axis. So like that. So all the people are on the rim, on the inside, and they're being pressed up against the wall, and they're going around horizontally. Now, I think they do make Gravitrons where eventually it'll actually tilt on you. We're not talking about that fancy kind of Gravitron. This is the county fair kind of Gravitron. Okay, let's take 15 more seconds. Okay, so one of the things I wanted to stress about this question, I don't want us to ever get the idea that normal is always up or anything. Normal is the supportive force from a surface. Normal is the supportive force from a surface. In this case, as you're going around, as these riders are going around in the Gravitron, something has to be pushing centripetally. So as I said, every one of these examples, that's what we're going to be asking. What is pushing centripetally? I think I can look at these people and know that the thing that's pushing them toward the center is the wall. That's their normal force. Their normal force is pushing them centripetally. In fact, one of the things I should probably stress right now is nothing is acting centrifugally. Nothing is pushing them outward. Now, if you were to put yourself in the perspective of any one of those riders, every one of those riders feels flung to the outside. That is a perspective thing. Similarly, when I'm driving down the road, my friends are in the back seat, and I take a sharp left, they get thrown to the right, right? What threw my friends to the right? Nothing. There's no force. Or when I take a really hard left in my car, and my friends feel pressed up against the right side of the car. What's pressing them against the wall? Nothing. There's no forces pushing you there. So that's a common misconception. I mean, similarly, you don't even have to be in the angular realm. If I'm sitting in my car and I hit the gas, I feel thrown backwards. What's throwing me backwards? Nothing. So those are all fictitious forces that we sort of invent. Something is throwing me backwards. It's actually you just have inertia and you want to stay going the same way you are, and something is trying to accelerate you. So in that case right there, each one of those people, they want to go in a straight line. And so constantly, as their bodies with their own inertia wants to go in a straight line, the wall is going, no you don't, no you don't, no you don't, and constantly accelerating them centripetally. So they're all experiencing a centripetal force. That's their normal. And the only thing holding them up, their weight is down. The only thing holding them up is the friction against the wall. So I guess it's B. Would be the right answer. And so if I'm designing a Gravitron, here's what I want to do. I know each one of my riders is going to have weight down. I need something up to cancel that weight out because I want to drop the floor. Something needs to hold them up. Well, the only thing holding them up, they're touching the wall. So my only thing I have at my disposal is friction force, because most of the riders are going to be parallel to the surface they're touching. So I need enough normal, because friction is the friction coefficient times the normal force. So I need enough normal force to stick them into the wall where the friction is sufficient. And so I just need to spin them fast enough, because imagine if you're the ride, if they're all standing there and the ride is stationary, the ride doesn't have to do any centripetal push. As it goes faster and faster and faster, it's harder and harder. There's more and more normal force, and eventually I can stick them on the wall. And I just have to get them going fast enough. Now the thing is, if I was designing one of these rides, you don't know what the two surfaces are going to be. You could make the inside of the ride out of metal or like gym mat or whatever, but you don't know what the other thing is. It could be big sweaty guy, and then that's going to reduce the amount of friction. So you have to take that into account. Okay. So Gravitron, an example of what is the thing pushing them, those people centripetally? It's the normal force. It's the actual wall. Let's kind of quickly go through a couple other examples. I guess pretty straightforward. If you've ever been driving down the road and taken a left or taken a right, if your path was somewhat circular, like most exit ramps and entrance ramps are, that portion, that picture, is going in a circle. Things in this universe don't go in circles by themselves. Something had to push on it. In the case of a satellite, the thing pushing it centripetally was its own weight. In the case of the Gravitron rider, the thing pushing centripetally was a wall. That Porsche has neither of those things available to it centripetally. That Porsche has weight, but the weight is down. The Porsche has a normal force, the normal's up. The only thing that is available to that Porsche in that picture to push centripetally is friction. So in that case, friction is the only thing that you have available to you to push you centripetally. So how fast you can go around a turn is limited, because if you want to go in a circle, you need something pushing you. You only have a certain amount of friction available to you. So your weight times whatever the friction coefficient is. So Porsche has pretty good tires, maybe a friction coefficient of like 0.9, I don't know. And so if you ever read like Car and Driver and they say this car has a lateral skid pad or lateral acceleration of something of like a G, that's a really good sports car, can pull a G. And what that means is it just has a friction coefficient of 1. And so if I can pull a G in my car, that means I can accelerate sideways at 9.8, which is pretty impressive. So you could put something against the wall of your car, and it would be pushed against the wall of the car the same as its own weight as you're going around the turn. That's pretty good. Most, I doubt my car could do that. Okay. Let's look at 3 more examples. We might have, okay. Got to get to some demos. I don't even know if we're going to get to them. 3 more examples, quick. If you ever watched a race car, I don't know if anyone have races buses, but if you ever watched like a race car, or even if you ran indoor track, you may have run on a banked track. Where's my track runners? And so that is when I want to go around a turn. If the Porsche that I had up there a second ago had only friction available to it. That bus in that picture has some component of its normal force also helping. And you could actually probably go fast enough. You could go fast enough. You could drive around a completely horizontal track. So that bus in that picture, the bus in that picture up there, has some component of its friction and some component of normal pushing it centripetally. So that bus could go faster in that picture on a banked track than it could around a horizontal track, because on a horizontal track, all you have available to you pushing you centripetally is friction force, whereas on a banked track, you're also getting some of your normal force. And a horizontally banked track, you can go as fast as you want until the track breaks, because the track is going to push you centripetally. And so, I don't know if you've ever seen, like, I think at a circus or something, there's guys that'll drive motorcycles around inside of a globe. I don't know if you've ever seen that, but no circus goers? Okay. Here's another example. This actually happened. There was a show called Fifth Gear, which is like a ripoff of Top Gear, which is like a British driving show. And these guys actually built a track, and they were able to drive a little Toyota in a loop-de-loop. And so let's talk about what is keeping that little Toyota on a circle. Things in this universe don't go in circles by themselves. Something had to push on it. If that Toyota goes crazy fast around that loop-de-loop, at the very top, where it is right now, there are two forces acting on it centripetally. Its own weight is always down. So at the top of the loop, weight is centripetal. Notice at the bottom, weight is centrifugal. Weight's always down. So at one particular spot, that spot, weight is centripetal. Weight is center-seeking. It's pointed toward the center. If it's going very fast, there's another force that's helping it stay on a circle, and that's the track. That's its normal force. So in that picture, he's probably going fast enough that he's got two things pushing him centripetally. He's got the weight of the track, of the loop, and he's got the force of the loop, the normal force, and he's also got his own weight. Now, there is a minimum speed that guy could go. So you can imagine he goes, if you were to try this experiment and go a little bit slower, a little bit slower, a little bit slower, there's going to be some speed where he just makes it around. And where he just makes it around, that minimum speed is the speed at which his weight is the only thing acting centripetally, where for just a split second, the track doesn't have to do anything. And so in fact, in this episode of Top Gear, they went to a physicist and they had a physicist figure out the math. How fast do I have to be going at the top? And so at the top, you can imagine the answer wasn't 0. If he's going 0 at the top, he just falls straight down. So there's some speed that if he was going a little too slow, he'd fall a little bit and then like hit in the corner or something. So there's this minimum speed where he's at the top, his weight is perfectly accelerating him centripetally. So when he's going in a circle, in the idea of just making it, you need to figure out how fast you need to be going such that your weight provides the centripetal force. There's a guy on a longboard. I think it's a little bit blurry. If you can see what's going on in that picture, he's kneeling. He's got red pants on. He's kneeling, and he's got a helmet on. And he actually rode a longboard, and they built out of wood a little loop-de-loop. The same deal. So in that picture, I think what's interesting, if you think about the rider on the loop-de-loop, he's riding on this longboard, and he's going straight at it. He's feeling 1 g of force. He's riding horizontally. It just feels like he does sitting still, constant velocity. Right when he gets to the ramp and he enters that circle, the ramp is actually trying to accelerate him centripetally. It's applying a centripetal force because he's no longer going in a straight line. He's now going in a circle. In order to go in a circle, you need something pushing centripetally. So all of a sudden, the ramp is pushing him centripetally or accelerating him centripetally. And you can imagine he feels heavier now. I think you can imagine that. So he's cruising along on his longboard, just feels normal. As soon as he's trying to accelerate on this circle, he feels much heavier because the ramp has to push him centripetally. And then he gets to the top, and if he's going fast enough, his own weight isn't enough to pull him down. His weight just keeps him on the circle, and he can make it all the way around. It's not exactly how it went. So what he didn't realize is that he actually there was a lot of force that was going to there was an equal and opposite force. So he's going in a straight line, no problem. In order to go in a circle that tight, something needs to be pushing in centripetally. And it goes up with the square of your velocity, by the way. So if you go faster and faster, that ramp needed to push a lot harder. And that ramp had to push very hard to keep him centripetal. What you just saw is an equal and opposite Newton's third law thing happening, and the ramp couldn't push hard enough. I think he pushed on the ramp pushed on him. The ramp didn't have much to push back on. and the wood broke, and it also moved on the surface of the road. So you can actually see that it moves pretty far. So they didn't secure it to the road enough, and it did break. Okay. I shouldn't laugh. Okay, let's see. I mean, it's pretty fun. Okay, one more example. One more example, and that is a rope swing. That's Miley Cyrus. So on a rope swing, and this is another good example. I won't show the video because the guys do get hurt. But on a rope swing is a similar example. So if you ever just hung on a rope like this, just grabbed and hung onto it, hopefully most people have the strength to do that. Where it gets disastrous, and YouTube was made for this, is where it gets disastrous is once you start swinging, how hard you have to hold on goes up with the square of your velocity. And so if you watch Betty White or anyone else go in a circle, nothing goes in circles in this universe. Something is pushing or pulling. In this case, it's the rope. So the rope is the thing that, if you're just hanging on there, the rope has to supply your own weight, which could be already pretty substantial. And then if you start moving in an arc, the rope has to hold your own weight plus the amount of force required to push you centripetally. And so if you've ever gone to a rope swing, like a lake or a river or something, and stepped off and gone on the rope swing, you might have noticed you have to hold on really hard. And YouTube is full of people that don't know that, and they don't even make it into the water because they don't realize that how hard they have to hold on is about to go up a lot. And so usually want something to sit on that makes it a little more likely that you'll make it. So in a rope swing, the thing that's acting centripetally is the rope. And the ropes are nice, that they're always pointed toward the center of the rotation, and so it'll work. This video that I saw the other day is some guys thought this would be a great idea where we could make a really big rope swing. So we're going to attach a rope to the middle of a bridge, and we're going to walk to the one end of the bridge with the rope, and the rope is now taut, and we're just going to step off the bridge, and we'll swing down. And they did it, and it was awesome. It was probably a really good rush. They swung down, made it almost to the other side, and then just swung, and eventually just dropped themselves into the river. And they said, that was pretty fun. I wonder if we could do it with 2 or 3 of us. And eventually they got up to 5. And so you've got 5 200-pound guys. It's 1,000 pounds. So they go to the rope store or whatever and say, well, there's 1,000 pounds of us. We want to be safe, so let's get a 2,000-pound rope. And so 1,000 pounds of guy could easily hang on a 2,000-pound rope. Factor safety of 2, no problem. Then they take these 6 guys, they all get together, and they step off the bridge, and they start swinging. The centripetal force at the bottom is much more than just their weight. The rope at the bottom has to counteract their own weight, that's one force, but also has to be the thing that is acting centripetally. It's gone up with the square of their velocity. All that potential is now gone into kinetic, and it's a lot. And so the rope lets go. And now they have no centripetal forces. The rope snaps. They have no centripetal forces. The only force they have is their own weight. And now they follow the path of a projectile, not the path of a circle. And so conveniently, it snaps right about at the bottom. And so what happens when the rope snaps at the bottom, you're traveling horizontally. An object in motion horizontally tends to stay in motion horizontally. And in the video, they just kept going sideways. And then eventually, they kind of arced and then kind of skipped a couple times on the water. And the next shot is the guy from the hospital going, that was a terrible idea. I now know a lot more about centripetal forces. Okay. I want to at least do, okay. I think what we're going to do today is maybe a couple demos, and then Friday we'll have to explain the physics behind the demos, because, yeah, we don't have time to actually, still have 5 minutes, don't start packing up yet, but I did want to at least do one demo today. Let's see. Which one? I think, yeah, okay. We'll do the easiest one. So right now, we probably only have time for one. The demo that I'd like to show, let's get through a couple. Okay, let's get through a couple. So here's one. So here's a potentially disastrous demo. Wine glass, actual 1990 French wine. Doesn't look like French wine, but we'll pretend. Okay. And this is potentially dangerous. So, bad. We'll see how this goes. Okay. So, I was going to try to get here early. I was going to try to get here early to practice this, and it didn't happen. So, what I hear, and I just Googled this, what I hear that the hard part's stopping it. And so that's class. See you Friday. No, just kidding. Okay. Okay. Thanks. So that was not attached. That was not attached to the plate. It's real glass, real liquid. So the only trick, and like I've said this before, I hate doing tricks. The only trick is getting that into a situation where it's going fast enough. It's going fast enough in a circle that its own weight is not accelerating it toward anything I don't want to accelerate it toward, like my head. So if I were just to take a glass of wine and put it over my head and let it go, it's going to accelerate down. That glass of wine was above my head and was subjected to only one force, its own weight. So therefore, it was accelerating toward my head. That's actually true. So if I were to take a glass of wine and let it go, it's going to accelerate toward my head. That glass of wine also was accelerating toward my head. But that acceleration, because it has sideways velocity, that acceleration only served to steer it and not reduce its radius. That's kind of a mouthful, so I want us to all understand that's what's going on. Same when you're driving your car. When you're driving your car in a straight line and you're turning, you are being accelerated toward the center of your turn. That doesn't mean you're going toward the center of your turn. It doesn't mean your distance to the center is being reduced at all. It just means you're taking a left or a right. So if my velocity is this, here's me with a velocity of this. If I accelerate now to the left, that just means I steered. I didn't slow down or speed up. I just steered. So in that situation, that's exactly what was going on. That wine glass was accelerating the whole time. But that acceleration did not serve to speed it up or slow it down. There's three ways you can accelerate. You can speed up, you can slow down, you can take a left or a right, you can turn. And so the weight of the wine and the glass, and probably also the tension, I could have gone the exact right speed, so at the top it would have been weightless. I'm not that brave, but I could have slowed it down where at the top the rope went a little slack, and just the weight of the wine glass, the wine itself, it was weightless a little bit, it would have felt weightless anyway, at the top, and then it would have come back down. And so I think that's our understanding, is that at the top, the weight and the tension did not bring it any closer to me, just steered it. And so I can carefully orchestrate a situation that looks kind of crazy like that, but that's really all that's going on. We'll get more into the physics behind that and also some other fun stuff Friday. Don't miss it.